Memoization. So what is memoization? So let us understand this from the perspective of design and analysis of algorithms. So in computer science there is a subject called as design and analysis of algorithms. In that subject we study different algorithm design strategies or algorithm analysis strategies. So there is one algorithm design strategy or paradigm called as dynamic programming. This extensively uses this memoization technique. So let us understand this memoization technique from by taking an example. So here is an example of Fibonacci series. Fibonacci series is a series of numbers which looks like this. The nth number here is equal to sum of previous two numbers. For example, this number is sum of these two numbers. This number is sum of these two numbers. That is how this series is generated. This series is called as Fibonacci series. So here is a recursive function, C function, to generate this nth Fibonacci number in this series. So this is a recursive function. Here I have a recursive call to the same function. Here I have a call to the same function. Right? Now if I call this function for computing 10th Fibonacci number, this is a function call. When I have this call, this complete code will be executed, right? So when I have this call is generating two more calls, because here n is equal to 10. I am passing 10 to this function, so n is equal to 10. N is neither 0 nor 1. So I'll be generating two calls from this function. The first call will be Fibonacci of 9 and the second call will be Fibonacci of 8. So this is a function call again. For this call I'll have to execute this complete code. For this call also I'll have to execute this complete code. So that is how the calls will be generated. And if you look at this tree, at the bottom of this tree or at the leaves of this tree, you will have only calls like fib of 0, fib of 1, fib of 0, fib of 1, etc. Right? Only fib 0 and fib 1. Okay, the point to note here is, if you look at the calls, there are many redundant calls. For example, you are generating fib of 8 here as well as here, right? So you are generating fib of 7 here, 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 again fib of 6 here, 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 right, here, in many places. And at the bottom or at the leaves, you see you have number of or many redundant calls, fib of 0, fib of 1, fib of 0, fib of. Now see, this call is a computation. This call is nothing but executing this function and all the function below this. For example, if I am executing this call, means I am executing this function once, as well as I am executing this code for all the calls below this fib 8, right? So that means this redundant computation is very, very, very expensive, right? So but you see, these are redundant calls. You are doing it here and here also, right? So this memoization talks about, right? Memoization talks about cutting these redundant calls, right? So when we come across some call or some computation for first time, so we'll do it. For example, I'm executing this fib of 8 for first time. So I'll execute it, and after executing this, I'll store the result of the computation or result of this fib 80 call, whatever may be the result. For example, if 8th Fibonacci number, I really don't have answer here, this is 0, 1, 2, 3, 4, 5, 6. 7th Fibonacci number will be sum of these two, that is 21, and 8th Fibonacci number will be sum of these two, that is 34, right? So answer of this will be 34. Once I get this answer, I'll store it, right? And later, when I come across the same call again, I will not do this computation again, but I'll use the result which already got from the previous computation, right? So that technique is called as storing and reusing, and that is the crux of memoization. Memoization says, if you come across a computation for first time, do it, store the result, and later if you come across the same call or same computation again, use the result from previous computation. So now imagine if I compute fib 8 here and store the result, And now if I am coming across fib 88 again here, right, and now here, rather than doing this see, in order to do this computation, I'll have to do this computation, I'll have to do this call, execute this call, then only I'll get the answer to this call, right? So when I come here, when I'm coming for fib of 8 for second time, I can use the result which I already got, right? Thus I can cut this entire computation, right, and save enormous time, right? That is the main idea or crux of memoization, right? Now that is compute once and reuse it, store and reuse. Now same function I can write by using the principle of memoization, which we use in dynamic programming. I can write the same function like this, right? Here we are using this array for storing the numbers. We are initializing these arrays. 0th Fibonacci number is 1, first Fibonacci number is also 1. That's why initialization is done to 1. And then from here onwards, just run this loop, right? And for computing any number, right, just add previous two numbers, right? The result of previous two number you already stored, computed and already stored here, right? So that is how we can use memoization, right? So now in our deep neural network, or in training of a multi-layer perceptron, which we already saw in the previous video. So this is a multi-layer perceptron, right? And when you are training this, you are calculating the weights, you are updating the weights. That is the meaning of training of a multi-layer perceptron. Now when you want to update any weight, you will need to compute the derivative of this loss function with respect to that weight. For example, if you want to update this weight, you need the derivative of this weight. Why? Because the formula for new W is equal to old W minus eta time derivative of loss with respect to that weight. So now in order to compute the derivative of loss with respect to this, we use chain rule, derivative of loss with respect to O31 and derivative of O31 with respect to this, right? So that is the chain rule I wrote here. Similarly, the formula for computing this derivative of loss with respect to this I wrote here. So again, this formula is computing the derivative of loss with respect to this weight. Because I want to update this weight, I'll need this derivative at the time of updating this weight. Similarly, this derivative for updating this weight, and this derivative for updating this weight. Now this is a relatively a small network, neural network. In practice, you have very deep or very large neural networks where you have a lot of weights, and that time you will need to compute many derivatives, and computing derivative is not an easy task, it's not a trivial task, right? But can I reduce this computation? Can I make it more efficient, right? If you look at these derivatives, I am computing derivative of loss with respect to O31 here, as well as here, right, as well as here, and here, right? You see, in only these 5 derivatives, right, I am doing this derivative computation repeatedly, right? This is redundancy. I can, if rather than computing, see, I am computing here as well as here as well as here, right? That means I am doing the same thing again and again. I can cut that time. So how can I cut that time? Again, once when I'm computing this for first time, I'll do the complete computation, right, and store the result. So I can store the result of this in here, let's say in this neuron. Let's say I can have a memory cell, and I can store this dou L by dou O31, right? So when you compute for the first time, do it and store the result, and later when you are coming when you want the same answer, use the previous result, right? So here, rather than doing this computation again, I can use the result from here. Here also I can use the result from here, so on and so forth. So we can compute the derivatives and store those and use those as and when required. So this is the crux of memoization, and that is how memoization is very useful in reducing the computation or making the computation very efficient.